Here to talk about FMA, fault management, I/O handling, all the great things that go along with that. Not exactly the most glorious part of any storage architecture, but certainly a very important one. So I thank you all for hanging out with me instead of going to listen about SSDs and cool hybrid storage pool stuff. So just a quick review. How many of you are familiar with FMA? Have you seen an FMA fault? Have you ever? Not much? All right, let me just do some quick terminology then. So FMA stands for the Fault Management Architecture on Solaris, and it covers all faults across the system, CPUs, memory, PCI, disks, ZFS, and all sorts of other stuff. Once you get into some of the stuff we've done in the Storage 7000 series, it includes services, you have power supplies and fans. Basically, anything that goes wrong on a system goes through this interface. And one of the fundamental concepts of FMA is to separate out errors and faults. So traditional systems, you get a bunch of syslog messages. Just I/O errors, or what you're looking at are individual errors that are symptomatic of some other problem. And it's up to the administrator to sit there and sort of divine what these things mean, like uncorrectable PCIe error on bus OX7E. What does that mean? Is my card broken? Is my motherboard broken? Is, what's going on here? So with FMA, we actually have a very rich set of telemetry that are recorded as part of e-reports or error reports from detectors. And then that is completely separate from the diagnosis of said faults. So we have FMD, the fault management daemon, which lives in userland and performs diagnosis on these e-reports. And because we have such rich telemetry, and we've sort of implemented this throughout the stack, it's not just a case of, I see this error, this equals that fault. We actually can do a much richer set of diagnosis where we see errors on a particular rank of a DIMM or on a chip select line, and then we can correlate that with particular pages in memory or particular cells or DIMMs on the motherboard, and give you a much richer diagnosis that results in this DIMM is bad. Instead of a bunch of memory CE errors in your log, we'll actually go and tell you, because one CE error is not so bad. Some atomic ray came through and struck one of your cells, not a big deal. If you get 100 of them, 1,000 of them, something's probably wrong. So the diagnosis sort of separates that out, and you get a very concise, clear answer. So the terminology we use is FRUs, ASRUs, and resources. A FRU is the field replaceable unit. That's the physical component that you would have to go replace if something were wrong. And ultimately, that's the most useful thing for an administrator. So when there's a fault, it says the FRU is your CPU or your DIMM, and that's what you go and replace. The ASRU is the automatic system recovery unit. That is the software abstraction that Solaris has created on top of that. So for example, a disk, the corollary of that is a device or ZFS VDEV. In memory, you have pages that are backed by a DIMM. And then the resource is the individual thing you're diagnosing. So if you look at a memory error, the resource might be a chip select line or a rank of the DIMM. The FRU would be the DIMM itself, and the ASRU would be the pages of memory associated with that. Everything in FMA is built off FMRIs, Fault Managed Resource Identifiers. They're associated with a scheme, and they look like a URL, pretty much. There's a couple different schemes. The most interesting one for administrators is the HC scheme, which describes the physical components of the topology. And when we talk about FRUs, they are exclusively expressed in terms of the HC topology. So rather than C0, T0, D0, we talk about chassis equals 0 / bay equals 4, which actually has meaning to someone looking at this box. And there's a label associated with that which corresponds to the silkscreen label on the box, so that you can actually tell when something goes wrong what is actually there. And then the software diagnosis lives up in FMD, and there's basically 3 different pieces of it. There's the diagnosis engines, which consume the e-reports and create faults associated with them. There are transport modules, which take telemetry from other sources and pull them into the FMA world. So for example, a disk may assert a smart predictive failure bit, and we'll convert that into an e-report by pulling the disks. Most of the time, e-reports are generated from stuff in the kernel, but you can also have transport modules, that live in user land. And finally, they're agents, which respond to faults and do various things. Typically, these are called retire agents, but they can do a bunch of different stuff. So for ZFS, for example, when a hot spare is activated, what's actually happening is a bunch of e-reports get generated, which results in a fault, and then the ZFS retire agent responds to that fault and does the spare itself. So there's no code in the kernel that understands how to do spares. From the kernel's perspective, it's just zpool replace of this thing that's a spare. Whether that came from an administrator or it came from FMD, I don't care. So that is the whirlwind tour. Apologies if it was a little quick, but we don't have a ton of time. So let's get talking about storage FMA, which covers a wide range of things. And this has really been sort of building up a lot in the past year. So some of the foundations, obviously FMA has been around since Solaris 10. There was some preliminary ZFS support in Solaris 10, in Solaris Nevada with the initial ZFS putback. But really it's the last year and a half where a lot of this stuff has become much more powerful. So at the core of it, from a storage perspective, is disk enumeration. That is, giving a physical location identity to resources. So like I said at the beginning, instead of C0, T0, D0, or for your MPXIO, C0D, some gobbledygook, SAS worldwide name, D0, you actually can get what chassis it in, what enclosure it is, what bay it is, and actually understand where this thing is happening. And there's two ways to enumerate things. One is, for most internal systems, we have to rely on a static XML file. So ideally, we would love to have something between SMBIOS and IPMI. It would be great if there was some way to say this phi hanging off of this controller corresponds to bay 4. But nobody in the platform world thinks about management in general, and that doesn't actually exist. So right now, we rely on static XML for internal bays. External enclosures is different. We have SES, which is the SCSI enclosure services, and a well-designed SES target can actually describe very well the physical layout of the box. In particular, you have drive bays, which are associated with the SAS address. And therefore, we can go through the Solaris device tree, find the devices that have that SAS address, and associate them with the physical bay in the box. So this lets us identify where things are. And then these are sort of the things we can do with it. So SCSI diagnosis is looking at basically the error cases from issuing SCSI commands, looking at check conditions, things with ASC and ASCQ set, figuring out what that means. So what we have in Open Solaris today is a very primitive version of this. There's obviously a lot of interesting stuff we can do here. And we've implemented pretty much the basic things, which is if a drive reports a fatal condition, which is some set of ASC and ASCQ values that I don't know off the top of my head, that'll result in a diagnosis. We don't do any CERT analysis. We don't watch a series of events and try to imply that a drive might be failing off of this. That's an area we want to go do, but is quite complicated. It gets difficult when you start to look at the entire I/O fabric as a whole. ZFS diagnosis is one of the more mature areas of the storage FMA strategy. So there we can detect devices which fail to open. We can watch checksum errors and I/O errors and tell when a device has failed. And there's what we call SERD, soft error rate discovery determination. Anyway, again, one checksum error not the end of the world. 1 I/O error, not the end of the world. If I see 10 I/O errors in a minute, that drive is going to be bad, or we want to stop using that drive. So we'll generate a fault diagnosis. The ZFS retire agent will tell ZFS, hey, don't use this anymore. Now, if there's no way to stop using that, let's say you're in a stripe config, or the other half of your mirror is offline, it'll just mark that degraded, because it's better to have some of your data than none of your data. But if you have replication, it'll mark it faulted, and ZFS will stop using it completely. There are a series of faults which have a one-to-one correspondence between ZFS world and the FMA world. So device fails to open, or the device is not functioning enough to read the identifying label off the device. In those cases, what basically happens is ZFS is the diagnosis engine and preemptively stops using it, because it knows it doesn't need to rely on user land to go and tell it and come back that it's not using it. Yep.
ZFS catches it, fault management.
Yeah. Well, and then FMA is just there to sort of as a way of telling the user what's happening and do things like hot spares and stuff. But it's not doing any active diagnosis there. It's like, ZFS told me this thing is completely busted. I'm letting you know it's completely busted. There's a second class, which is I/O errors and checksum errors, where if the device continues to operate but is just generating errors, that's where FMA does a more complicated diagnosis and comes back. And right now, that diagnosis, complicated might be a stretch. It's pretty simple. It's just a CERT engine with a number. Ideally, we'd like to look at things like bad blocks, areas of disks that are bad, instead of the simple thing we have right now. In particular, if you have one bad block and you're hammering it, and attempts to repair it are failing, then that one bad block, if you access it fast enough, generates enough I/O errors that it thinks the disk itself is bad. So there's areas that we want to do there, enhance there, but it can get, again, complicated, as all things can with FMA. There's basic smart monitoring in there today. So this is the disk transport module, basically once an hour. It's a very primitive module. Once an hour, looks over all your disks, checks for overtemp, self-test failure, as well as the predictive self-failure bit. So SMART as a whole is sort of this very wide-ranging way of exposing error counters to consumers. However, there's no schema or no well-defined schema associated with them. There are lots of vendor-specific stuff. There are various open source libraries out there that have a bunch of tables that know this drive vendor equals that. And drive vendors like to keep that very secret because they don't want customers inferring that a drive is broken when it's not. So that's why the only publicly available thing is a single bit that says, I think I'm failing. And it is up to the drive firmware to report that. And that way, the vendor, when they get a drive return saying this is broken, they go look at that bit. If it's not set, they assume it goes into a different bucket. It says run some more tests. Where if that bit is set, then they don't have to do any more work there. There's some work that's coming up to make this a little smarter. So right now, opening every device once an hour can be a little disruptive, especially if you're trying to do power management. And it also rescans your world every time a new disk is inserted or removed. So there's some work to integrate that more closely with the kernel in line, because these can also be returned as part of check condition codes and stuff like that, just in band with the I/O instead of having to sit there polling. Then we get into things not related directly to disks, but more in enclosure management, but also quite important. So LED management, in general, this is the faulted LED. There's also the Identify LED, which FMA doesn't use. But for example, in the Sun Storage 7000, we let you turn it on and look at it. And there's the OK to remove LED, which I think is completely stupid and we don't use in the 7000 series. That is, if you're not designing a system that can support surprise removal at any time effectively, then don't come and play. I mean, that's the world we live in. So the idea that I need to config ADM-C, unconfigure this drive, and then the little OK to remove LED comes on, and then I can walk up and pull it out, that's So 10 years ago or 20 years ago. So I personally don't care about that. So this really comes down to just the faulted LED. PSU fan monitoring, both for internal systems and external enclosures, is another thing that's, it's part of the enclosure, it's part of the system, it affects how things work. So we want to be able to detect failure there. And again, this is easy if you hard code a bunch of things in a .c file, hard if you want to do it generically. So libtopo exports an abstraction of sensors that we can then monitor and look for failure and not have to know that on this platform, if the ps0.vinok generic device locator record is asserted, that means this power supply has failed, right? That's all hidden inside of the XML GUI up here so that you can write generic stuff to consume it. The only thing I'll point out on this slide then is that these two things have no lines over here. That is, we don't really do any diagnosis at the HBA or I/O fabric layer. This one in particular, super hard. So I don't have time to go over this, but this I already talked about this, how one side can go down IPMI, another can go down SES. FMD doesn't care. It just talks to libtopo, and all that abstraction goes away. This I want to mention quickly because there's been a lot of griping about this on various Open Solaris aliases. This is basically how, so Jeff Bonwick rewrote this in build 103, and this, for those of you who are paying attention on the ZFS discuss list or just way too involved with Solaris code, this corresponds to the fail fast flag, which means don't try hard. Like, don't wait for the device. If it doesn't come back immediately, don't do anything. So if you have a device that is misbehaving but is otherwise responding to requests, in the old way, you would have a mirror of A and B, where B is perfectly good, A is being a bad citizen. And in the old world, we'd first try A, and then we'd try really hard with A before we even went to B. And this results in stalls and hangs throughout the ZIO pipeline, pushing that up to the pool level. In the new world, we try all possibilities in the fast mode. Actually, this arrow is wrong. That should be over there. We try all possibilities with B fail fast set, and only then, if everything fails, do we go back and try really hard. And for writes, instead of trying really hard to write it to here, we'll just go write it somewhere else, assuming you have multiple top-level VDEVs. And basically, this will eliminate the vast majority of cases where you see stalls and hangs. And you can thank Jeff for that. OK, in the last 1 minute, stuff that I have not yet put back to Open Solaris. Things sitting in my workspaces. Generic FRU monitoring. Right now, we talked about the LEDs. In Open Solaris, that only works on the 4500 and 4540. Does not work for external enclosures or other platforms. This exists in our gate. I'm trying to get someone on the FMA team to put it back, and it should hopefully happen soon. ZFS Auto Replace is a feature I put back a basic version of a long time ago, but only works with SATA devices. Doesn't work with MPT or MPXIO. In the Sun Storage 7000 series, I've basically fixed that using this work. And when you set this, this basically means this device is associated with the physical slot. If you go up there, physically remove it, put in another disk, the system triggers all of the ZFS zpool replace code to go and do the right thing. And that works even if you have MPXIO and multiple paths and stuff like that. Very handy. ZFS faults with FRUs. Right now in Open Solaris, you get a ZFS fault. All it says is VDEV OX74ZDE is faulted. And you have to go type zpool status and figure out what that is. In the 7000 series, soon to come to Open Solaris, there's actually a FRU associated with that. So instead of just getting that, it'll tell you disk 47 of storage enclosure, whatever, is failed. And along those lines, there's what we call message ID argument substitution, which right now, those messages that gets printed in the syslog just say, a disk has failed on the system. A CPU has failed on the system, because there's no way to parameterize those messages based on the fault. This lets you do that. So now it says the disk in slot, bay 47, has experienced unrecoverable I/O errors and has now failed. That one is being worked on right now and will be back very soon. However, without this one, it's not very interesting from a storage perspective. So 30 seconds over, but future things we're going to do. I/O fabric diagnosis. Incredibly difficult. There's some basic stuff we can do with SMP, which is the SAS management protocol, such as detecting when one lane of a physical connection is down. That's something that's easy. An example of something very hard that we would like to do but may never do is, I know from SMP that I have a connection to this expander. However, I can see no disks behind it that it claims to talk to. That would be an example of a more complicated diagnosis that we'd love to do someday, but is very hard. I talked about the improved smart monitoring. Another hot topic on ZFS Discuss is recovering from previous view as ZFS Uber blocks, which Jeff Bonwick's working on right now. This is where ZFS assumes that disks behave according to how they should behave. That is, if they have a write cache, that flushing the write cache will actually do the right thing and that it will preserve write semantics, write ordering. If it doesn't have a write cache, then it's not going to cache things. But with very low-level consumer grade disks, that's not actually true. And right now, you can get in states where your pool comes up corrupted because the disks lied about their consistency. And it's basically impossible to implement a transactional file system on top of it. Not basically, it is impossible to implement a transactional file system on top of that. What this lets you do is say, oh yeah, go back 5 seconds, 10 seconds, 15 seconds until you can find a consistent copy and let me use that. That is, I would rather have some of my data than none of it. So that's coming. This is another one that comes up on ZFS Discuss. If you have a stripe or you lose both sides of a mirror, right now the pool will come up faulted, even though with ditto blocks and replication of data. So metadata gets stored in multiple locations on the pool. We should be able to get you the majority of your data, even if, let's say I have a stripe of A and B, no mirroring. If I lose B, we should be able to get you half your data, right? Because the metadata was written to both. But right now, the pool just comes up faulted and no dice.